All right, well, welcome to the last week of modern physics. We have a little bit to, to finish up here. We're still talking about nuclear reactions. Last time, I know it was a while ago because we took an exam, but last time we were talking about the radioactive decay, the decay processes in the nucleus, and those are nuclear reactions, right? Where we release the alpha particles and the beta particles and the gamma waves. But we also need to talk about kind of the two bigger ones, fission and fusion. Seeing those are, I don't know, what makes all of life possible on Earth. We should probably talk a little bit about those. And then we'll start talking about even smaller particles. All the weird things like, I've already talked about neutrinos, but we'll also talk about all kinds of other things that are out there. There are all kinds of little creatures that actually build up a lot of the other particles like protons and neutrons. So we'll start talking about those and just sort of start piecing it all together. All right. So let's start by talking fission and fusion. All right. So these are the two primary ways that we can actually create energy through nuclear reactions. When we were talking about the radioactive particles, we're not necessarily creating energy. Sometimes we are, but for the most part, it's just things are changing in the nucleus. We're releasing particles as we do so, right? But these other events, these are actually what power things like stars and all that. So let's start with fission. Right. All right. Now, here's what happens with fission. Suppose that we've got a nucleus of some type that's sitting here doing its thing, and it gets hit by a really energetic particle. Now, you can think of this nucleus. All right, so here's what happens. This energetic particle comes in and hits it. Usually, these are neutrons, but it can actually be other things as well. But usually, it's a neutron. So suppose we have a neutron comes flying in here and slams into this particle. Now, if we were talking about like big objects, like this is a planet and we send, an asteroid towards it or something, right? What do you expect to see happen?
At that size, damage.
Okay, so we would see damage, right? If it was big enough, what else could happen?
Could alter orbit.
All right, it could alter its orbit. If it was really big enough, it could just, break it in pieces, right? But we should expect, like, depending upon how much energy this thing has coming in, it could actually cause some significant, let's say, quote unquote, damage. Now, when fission occurs, what happens is this neutron comes in and literally breaks this into two smaller nuclei. So we have one parent and we end up with two daughters. Now, what's really going on here? Think of this as a potential barrier kind of deal, where that parent was originally made up of those two daughters. So we have like two daughter particles within this parent nucleus. Kind of think of it that way. And there is a potential well trying to hold them together, right? Like if we do our whole, like, here's radius away or whatever, they want to be trapped in here because of the strong nuclear force. And they've got some amount of energy, right? Let's just say that the baseline of energy is here. And clearly there is the possibility that they could just split apart normally. But this neutron comes in and gives it a little bit of extra energy. if it's energetic enough, we've now bumped up here, and you notice that the gap to the top is way less. And so basically what happens here is this neutron is energetic enough to create enough increase in energy that allows the daughters to separate from each other. And that's what happens with fission. We're actually taking the nucleus and we're breaking it in two. Now, when this happens, there is the possibility that more energy is released than energy that was brought in. Can you kind of see why? I mean, my graph kind of almost even shows it, right? Like this was the added energy. But then we get back down to, let's say here, there was this change in energy right here, right? So it doesn't quite add up in terms of the amount of energy that's completely released versus how much was added. And so there is a bonus amount of energy. All right, now here's the kicker though. When this happens, when fission happens, you'll get your two daughters, but at the same time, you'll get some more neutrons flying out. They often get stripped from the daughters. So the daughters will still have the same number of protons. So whatever the parent was, if the parent had, let's say, 68 protons, the daughters between them are going to have 68. They may not be exactly the same. And in fact, they're usually not. They're usually not identical to each other. But they'll still have the same number of protons. But then depending upon what isotope we have and how many neutrons there are, it's often that we'll get other neutrons that are kicked out. All right, now suppose we have more than just the one parent. Okay, so we got a bunch of these guys that are out and about, and in general, that is the case, right? It's not often we have just one atom of, insert your favorite material here, but we have a whole bunch. Okay, so here comes a neutron, comes in and hits this guy. And this goes through a fusion process. At the same time, it releases a couple of neutrons. Well, those neutrons can come in, hit other ones, and cause fission, which then releases more neutrons. Those neutrons hit other particles, and we get what's called a chain reaction. And this is what happens in nuclear power plants, right? So when we've got a nuclear power plant, even just one like this is a small that fits on a submarine, for example, this is what's going on. We get controlled reactions by having this fission occur. We get extra neutrons that are kicked out. Those neutrons then cause more fission events, which create more neutrons, which create more fission events, and chain reaction. All right, so we can actually get a lot of energy released from this one fission reaction if we can have a good enough cascade. But you can also see the potential problem, right? What if we start kicking off too many neutrons and we have too many of these things start splitting and we create too much energy? Well, that's where we have things like control rods. That's where those come into play. If you've heard that term, control rods, these are, they literally are rods. I think they're usually made out of graphite that are put in to help slow the neutrons, right? If I were to put something in between here, so we'll put a little shield, But this shield doesn't necessarily stop the neutron. But what if it just slows it down? Well, if it slows it down enough, even if it impacts, it's not going to be able to increase energy enough to really make it that those daughter nuclei want to or can split apart through that barrier. Right? So they will put other material in there to act as a medium to slow down the neutrons so that they don't cause future fission events. So it's all a balance. Like in a nuclear reactor, they want to have enough neutrons that are coming up with enough speed to create this sustained reaction. Right? So you don't want to slow them down too much, but you also don't want to let it just go without being controlled. Because when that happens, that's when we have meltdown. Right? Like you remember what happened in Japan, what was that, about 10 years ago? I think, right? Or Chernobyl back in the 80s. Oh, great little mini series, by the way. If you haven't seen Chernobyl, you should check that out. But anyway, in that case, it just keeps going, going, going. You get insane amounts of energy, and then we have a problem, right? Way too much energy, and it literally causes the equipment to start melting, the containment to fall apart, and we're done. Ralph, that's a good question. I'm trying to remember where I saw it. I don't think it's on Netflix. I think you might be able to find it. Was on maybe HBO when they first did it, so you might be able to find it on HBO Max, but I'm not really sure. It just, do a search for Chernobyl. It'll I'm sure you'll be able to find it pretty quickly. Anyway.
I have a question.
Yeah.
Is this a form of decay?
I guess you could say, yeah, I guess. We don't usually think of it as decay because we're actually producing multiple daughters. Like in a regular decay process, you just have your one atom going to another form as it releases alpha or beta particles. And in this case, we're actually breaking it into two, which is a very different thing, right? Like if now all of a sudden we have two different nuclei, as opposed to just the one nucleus has changed and it's different. So I've never heard it classified as decay. I don't think of it as decay, but it is a nuclear reaction, just like decay is a nuclear reaction. But it really is a different type because there's a different result, right? Going from one thing to two things is a little bit different than going from one thing to a different one thing. Yes, we are releasing particles at the same time, but it's I would say it's a very different process. Anyway, I've never heard it classified as decay, so I'm not going to call it that either. All right. Well, anyway, so that's what fission is doing. So when you hear about nuclear fission, that's what's happening. Here's a little fun story about fission as well. Like when they were first playing with the idea of fission, and they did their first chain reaction. This was in Chicago back in the 40s. The Manhattan Project. It was actually under a football stadium. You gotta love it. They built their nuclear reactor under a football stadium. I think it was the University of Chicago. But they were a little concerned that if they started a fission reaction, that it would never end. That while they might go through all the material that's in their little pile of stuff, well, but what about all of the nuclei that make up the air.
So they thought it would have spread to other pieces of matter just around it.
Yeah. Yep.
Wow, that's terrifying.
Yeah, and you can imagine when they were first doing this, they're like, okay, are we dooming the Earth,
All life on planet.
right? And they still decided to do it anyway because got to beat the Nazis or whatever. Um, but there was some concern that there was the potential that it could just cascade and continue cascading. But I think they were right in assuming that the density of material elsewhere wasn't such that it was going to allow this really to happen. Right? Because I mean, think about the picture that I just drew here with all the neutrons flying off. There obviously have to be other particles for them to run into, and if this is like really sparsely populated, oh, those neutrons are just gonna miss. They're not gonna hit anything, and then even if they do, they're gonna lose a lot of energy as they're flying through space, and But that was one of their concerns, and um, I'm glad that that's not what happened. Um, but yeah, you never really know. That was just reminded of a book called Cat's Cradle by Kurt Vonnegut. I don't know if any of you guys have ever heard of that or read that one.
That's the one with Ice Nine, right?
Yep. That's the one where there's this thing called Ice Nine, which somebody figures out a way to create ice packed in a different way, and so it's Ice Nine. But the problem is that Ice Nine just kept spreading. As it went, it just like started freezing everything. So, spoiler alert: the Earth gets doomed by Ice Nine. But anyway, be careful with your power. That's all I'm saying.
So, I mean, theoretically, though, if you had, you're on a planet with a super dense atmosphere, it could be possible to just piggyback and continue.
Yeah, and if the isotopes that made up the atmosphere were such that they were easily energized to a point where they could split. Let's put it that way. And it becomes less likely every time you create these new daughters. Those daughters are less likely to go through another fission event because they're like, you have to have a certain ratio of neutrons to protons. You have to have a fair number of neutrons. But just think about this. If we've got the set number of neutrons and then we come in and bombard and we split, and some of those neutrons trickle away, well, now these two separate ones are going to have a much smaller neutron to proton ratio, which is going to make them less likely to go through a fission event. So you'd have to have the exact right wrong conditions for that to happen. But it's possible. Highly unlikely, but possible.
It's still terrifying.
It's a scary thought for sure.
Well, at least they managed to develop something that could destroy the world anyway.
Yeah.
Nuclear bombs.
Yeah, right. Who needs to have a non-controlled that goes on forever? We'll just have a really crazy strong controlled one and go from there. Right? Like you look at the amount of energy that those even the very earliest nuclear bombs could do. It's insane. It's an insane amount of energy.
And we dropped 2 of them. That's what blows my mind too.
We did. Yep. I actually do want to visit Hiroshima just to, to honor those, I guess, but to honor those people. But it's also interesting to see how much it has recovered, because now that was back in 1945, so we're almost 80 years ago. right? I'd be interested to see how much it's recovered, but I also would be kind of interested to in walking around the site around Chernobyl. That one is a little too fresh for me, though. I know that all the dust and dirt there is still pretty highly radioactive. So
Why is that? Why is Chernobyl still like so? It has such a large exclusionary zone. While I mean, you're able to visit Hiroshima nowadays, right? So
yeah.
why is
Well,
Chernobyl so much different?
So first of all, just think volume, right? The amount of actual radioactive material in those first nuclear bombs, pretty tiny, right? And I think also the material is different. I think what was being used in Chernobyl has much greater half-life than the materials that were used in Fat Man and Little Boy. But that I'm not sure of. But for sure, just volume. There was way more nuclear material, radioactive material at Chernobyl than was, I mean, like huge orders of magnitude more. And they also didn't do a very good job of containing it. The Soviets weren't exactly prepared for what happened, and their first responses were actually bad when it came to trying to contain what was going on. So, but that's about all I know actually about that. But and more time, right? Even with long half-lives, as time goes on, the material becomes less concentrated, and it also like drifts away, right? The wind carries it elsewhere. Like think about the Fukuyama. There was stuff that made it through ocean currents over to North America, right? So you've got that too. So if you think about like Hiroshima and Nagasaki, like a lot of that stuff got diluted basically by air, wind, water, whatever, moving it around.
Yeah, I remember they were encouraging people to eat iodized table salt, at a higher concentration than they normally would in order to help mitigate the presence of all the fallout that had blown over.
Yep. And when Chernobyl happened, I was living in Seattle area up in Washington State, and in a real agricultural area, and there was concern that because the kind of the global air current pattern takes a lot of the air from that part of Russia and brings it to I think technically Ukraine, but carries over to the Northwest United States. And so there were people that were concerned about like the strawberry farmers and all that were like, are we going to have, strawberries that are building up radioactive material because they're absorbing it through all the stuff that is falling down from the atmosphere and all that. I think pretty quickly it was determined that the concentration of that material was pretty minimal, and so it wasn't actually a problem. But it was something we were thinking about, and we were halfway around the world, So it's kind of a frightening thing, right? When you think about it, but at the same time, we get huge bang for our buck with this stuff.
Yeah, but is it like, is the gain worth the cost? Potential cost, anyway.
That is absolutely the question. And I mean, that's the question for all energy, right? Like think about how else we get electricity. And you go to things like, okay, well, what about the power plants that are building, burning coal and oil and whatnot? There's a cost to that, right? You're depleting those natural resources, and you've got some pretty significant pollution of a different type, right? And then you go, okay, well then what about like solar? Well, solar panels are great and all, but there is the cost of making them, and I don't just mean monetary cost, but Some of the things that we put into solar panels are not so nice for the environment. And if we start putting, lots of solar panels out, at some point we start changing the reflectivity of the ground, and that can have some significant consequences, right? If more of the thermal energy is getting bounced back into the atmosphere instead of getting absorbed into the earth. So albedo effects, so those reflective effects, are a thing. And Victor, yeah, you're right. They require a lot of surface area, which, now you're going to be damaging any kind of plant and animal life that normally would be getting the sunlight. So there's a cost there. But that's a legit question, and that's a question we should ask about any of this stuff.
See, the whole solar panel thing, I didn't even think about the reflectivity of it.
Yeah, I hadn't even considered that,
I hadn't
honestly.
considered that at all. I was thinking more along the lines of like lithium batteries. Have you seen a lithium mine before?
Have I seen what about them?
Just a lithium mine in general.
No.
They're gnarly.
Yeah.
They're gnarly.
I can imagine. So it's one of those things that, and this is where the scientist in me, when I hear the like super environmental people and they talking about this, that, and the other thing, and I'm like, well, got to be careful, because there's a cost to everything. There's a trade-off, and it's honestly, the answer, the best answer is minimize energy usage, right? If you're not using energy, we don't have to worry about where it's coming from. But there are also some like real passive things that we can do. Like think about the, I don't know if anybody has a solar water heater, but basically all you need there, like you could create just tubes that are up on your roof that water goes through, that just because it's sitting there, it's getting warmed up by the absorption of thermal energy. It's got minimal impact other than the material that makes the pipes. And you can make the, minimal reflectivity and all that as well. And then next thing you know, you've got hot water. But if the sun isn't out, you're not going to have hot water, right? So, but there are things like that. I think, me personally, the way to go if we want to try to deal with energy issues is, one, cut back on the energy usage, right? But then try to do more of those passive things that don't require the either huge upfront costs, because that's the other thing. Like you think about how much energy is actually needed to produce a solar panel. Do you end up getting that much energy from the sun before it craps out? I don't know. I think nowadays they are a positive return, but not by much, but even a small positive is better than no positive, right? But anyway, so minimize energy use and try to do things more passively. But it's a tough question, and it's just one of many questions and issues that we have to deal with the population of the Earth growing, right? I mean, that's the scary thing to me as a scientist, and a math guy specifically. I look at how the population number is going, and I'm like, man, the Earth is in trouble. The Earth isn't in trouble. Humans are in trouble, because it's going to get bad in terms of resources, and we're already seeing it, right? We're seeing, people in places fighting over food and water and space, and it's only going to get worse as we get more and more people. But, I'll be dead in 50 years, so it doesn't matter. I'll leave it to you guys to worry about. This is what
like
you say.
every
Okay,
other
boomer.
generation before. Yeah.
Yeah, it's like, okay, boomer.
Yeah, I'll let my kids take care of it.
Yeah. No, I joke, of course, because I think we should all be concerned about it, because we're all part of this. But you know, in the end, there's only so much I can do, but no, I do things, you know, but I still like having my air conditioning though. I still like, you know, taking a trip and going to Guatemala to meet all the people down there and experience that part of the world. And, you know, so it's not like I'm not going to do anything. If we all do a little bit, it can add up, right? Anyway, I'm starting to preach. So let's move off of fission and let's talk real quick about fusion, because fusion's the other big one. So let me clear this real quick. All right, so then we have fusion. Now, fusion kind of goes the other way. Instead of taking one nucleus and breaking it apart, with fusion, we actually are going to have two nuclei that are going to come together and get stuck together and form a larger nucleus. So this would be a case where you have two parents that form one daughter, right? As opposed to fission, where we had one parent creating two daughters. We're kind of going the other way. Now, this one, I think, is a little bit harder to see how we get energy out of this. Because think about the other one. When we had fission, when we split this into two pieces and stuff goes flying off, and you go, okay, well, to get energy, that means there has to be a loss of mass. And you go, yeah, okay, so you have these two things break apart, stuff goes flying, you lose some mass. Totally makes sense. But now fusion, we've got these two things that we're bringing together, and yet there's still a loss of mass. And that doesn't sit well. But hopefully you remember when we were talking about this stuff, like at the very beginning, when we ran into E equals mc squared and all that. There's rest energy, but there's also like binding energies and all that sort of stuff. And what we often get is that the sum of the pieces does not equal the whole. And that's what happens here. When we have fusion, we actually have these two things, when they come together, they form something that has smaller mass because of things like rest energies and binding energy and the like. So when we actually look at this stuff in this quantum relativistic world, it is possible to put two things together and get something smaller. And that's what happens in fusion. Now, you can't fuse everything. Like it's not possible to fuse everything. But fusion does happen and does release energy. And a great example is in the sun, because this is really where most of the energy comes from the sun. The sun is a huge fusion engine. All right, so here's an example of fusion process. So here's what we're going to do. We're going to let's suppose we have just two hydrogen nuclei that are coming together. Okay, so remember what hydrogen was, just plain old hydrogen. It's got a Z number of 1, because there's one proton. And what's its A number? How many nucleons are in a hydrogen?
Depends, but usually 1.
Okay, yeah, so it does depend which isotope, but just plain old hydrogen is 1. Okay, so hydrogen's just good old 1, 1. Okay, so then we're adding that to another 1, 1 hydrogen. Now, when these guys fuse together, they actually form another hydrogen. But this hydrogen is a heavy hydrogen. So it actually has neutron in there. And I know what you're thinking. Where the hell did that neutron come from? Because think about what we've got. If we just look at, let's make a list of our nucleons. We've got a proton. This one's got a proton. So we have 2 protons. But now we've got a proton, that's the hydrogen, but it's heavy. So we got a neutron. Okay. Where have we seen that before? Where protons turn into neutrons?
Decay.
Okay, which kind of decay?
Beta decay.
All right, so that was beta decay. Beta decay was where we had either a proton turn into a neutron or a neutron turn into a proton. And so if we kind of look at this, what's the total charge now?
It's still 1, right?
Okay, so it's +1, but we started with +2. So that means there needs to be still something with positive charge. So there's going to be a positron. So that's what happened with, so this is a beta decay is occurring as we're putting these together as well. Now, do you remember what else showed up in a beta decay? There's another little particle.
Electrons can also, oh wait, no, neutrinos.
Okay, so then we had neutrinos, and so we'll put a little neutrino here. So when we have 2 hydrogen nuclei fused together, they form a heavy hydrogen. I think it's called deuterium. But they also release a positron and a neutrino. And then there's energy. So some energy gets released as well. Now, this is actually just the start of all of this, because then that heavy hydrogen gets fused with another regular hydrogen. And this turns into a helium. And again, if you kind of follow what's going on, we got a proton and a neutron. This has a proton, so we have 2 protons and a neutron. Well, that's your helium-3, 2 protons plus 1 neutron for 3 nucleons. So there aren't any other particles released, but you will get a gamma ray. So you'll get gamma decay and more energy. All right, so we're still not done though, because in the sun, this continues a bit more. Now we're going to take 2 of these heliums and they're going to fuse together. But they actually fuse into helium-4. Now, if you're keeping count, and hopefully you are, this had 2 protons and 1 neutron. This has 2 protons and 1 neutron. This has 2 protons and 2 neutrons. So we're still missing 2 protons. Well, those 2 protons, they're just hydrogen nuclei. And again, plus energy.
When you say 1 neutron, you mean 1 extra than there should be?
Nope, I mean there's 1 neutron.
Oh yeah, I see. That's right.
Right.
I remember.
That's what that 3 is telling us, is the total number of nucleons.
Mm-hmm.
So it's that isotope. Okay, so Now, if we kind of take stock of where we are, this guy right here, this is an alpha particle, but this is stable. Okay, that's a stable helium. We also know it as an alpha particle. Along the way, we've had a release of energy 3 times. Some other little particles that are going to do whatever they do. I mean, the gamma ray might actually allow for some more energy coming from something else later. Same thing, like this positron might hit an electron and they might, destroy each other. Not annihilation will create energy. Right? Anyway, so some other things can occur as well. But notice we started with just protons, aka hydrogen nuclei, and we ended up with a stable helium and more protons. Well, those protons are ready to get involved and start doing this again. And before you look at this and go, oh man, this is awesome, it's just like never-ending cycle. And it's not quite true. Because look at the total cost here. If I want to get to this point where I've got my helium and my 2 hydrogens, how many hydrogens did we actually have to go through? Well, we need to create 2 of these heavy heliums. Each of those heavy heliums needed a heavy hydrogen plus a regular hydrogen. But the heavy hydrogen came from regular hydrogens. So it turns out that you need 3 hydrogens to make this helium. So another 3 are going to allow this total cycle. So we actually use 6 H1s, and those get converted into 1 helium-4 plus 2 H1s plus other stuff. A couple of positrons, some gamma rays, some neutrinos, and a bunch of energy. So I'm just going to put other stuff and energy. But this is the cycle that happens in the sun. And it's kind of cool how this all plays out in the sun, because if you think about the sun and what's going on here, okay, so here's our sun. When these events occur, when these fusion events occur, they are making the material in here want to go outward. Okay, so fusion is trying to push things outward. They get fused together, explosion, big energy gets sent out. All right, but obviously the sun doesn't break apart. Why not?
Its gravitational acceleration is pretty high.
Yeah.
That's one thing.
Because we also then have gravity that's trying to pull stuff back together. So that's what actually allows it to actually stay as one, in one big chunk, right? The gravity brings everything together and creates those forces that allows those hydrogens to get past the point of being repelled, because they want to be repelled, right? Like at this very beginning, remember, this is a plus. Those things are both plus. And yet we're able to get them close enough to fight that, to get past the Coulomb force, so that the strong nuclear force takes over and links them together. Well, there's an intense amount of pressure at the center of the sun. Think about all the mass of all of the sun and gravity pushing it back in. The center of the sun is just going to be incredibly high pressure, which means there's going to be a crap ton of fusion going on, which means a lot of energy being created. which means life on Earth exists. Right? So if it weren't for the sun and that amazing fusion engine that it has, none of us would exist.
And that would explain why once it starts fusing, even heavier things, it expands its surface area.
Correct.
But
And
why does it stop eventually producing energy? Like, why can't
Too
you
much.
fuse heavier stuff?
It's too
okay,
much.
and I remember we were going to talk about this because you asked about this. I forget when it was, Jacob, but you asked a while ago, right? When
Yeah,
we were
I think it
talking
was
about-
last Tuesday.
maybe last week or maybe a little bit before, but you get to that point where you go, okay, so we start getting more and more and more of these heavier and heavier things, right? Because now you'll get these heliums. The heliums get pushed together, they get fused into beryllium, right? And then you can get the berylliums fused together, or a beryllium gets fused with one of these heliums, and I think that makes carbon, right? And then a carbon and a helium makes oxygen. And so there's definitely enough pressure and all that to start putting these things together. But eventually, even these heavier things, they make their way out towards the outer, edge of the sun. The other thing that goes on in the sun is you've got convection cells. You remember convection, right? Like with the boiling water, where you'll get stuff that comes from from down below up to the top and then around and then back. You get these convection cells. Same thing's happening in the sun and in other stars. And so even some of these heavier things will get brought out here and then get ejected. And so slowly, material from the stars start getting ejected out into space. Right? So you'll start getting heavier and heavier and heavier things that are out there. So that's happening. But then also think about this. What are you going to need to do once we start getting heavy atoms, right? Like we start getting into the metals. So think now we're past all the gases, and now we're into like the sodiums and the silicons and all those kind of heavier deals. Think about what's going to happen now. You've got these much bigger nuclei that are being forced together. You need more pressure, first of all, to get them together. But then when they fuse, they actually release a lot more energy. Right? And so you start getting explosions. And then what gets crazy is when you get to iron, and here's what's weird about iron. For whatever reason, I don't know exactly why this is, but iron is such that in order to produce fusion, you actually need more energy than what gets released. All right, so now it's endothermic instead of exothermic. And the same thing with fission. You want to break iron apart, you actually need more energy than you get released. So as we start getting heavier and heavier and heavier and heavier, when we finally reach the point where we get iron, well, we're screwed. Because iron isn't going to fuse, it isn't going to go through a fission process without extra help. But we know that the universe doesn't like to give us extra help, right? The universe is always trying to minimize energy. So the universe isn't going to do something that requires extra energy. So once we get to the point where we get irons, your star is done. Anyway, so that's why they call it the iron catastrophe, because you get to the point where, well, nothing else is going to happen. Now, obviously, there are things out there in the universe that are heavier than iron, right? But there are some stars that can still fuse iron. I just think about what that's going to require. It's going to require way more pressure, way more heat energy, and all that kind of stuff at the center, which is possible to do, but you need to have bigger stars.
Don't they think that elements heavier than iron are only produced like through neutron stars and their collisions and stuff?
Yeah, you
Yeah.
start getting like crazy big impacts, and that extra energy then can get put into the fusion process, right? So yeah, but that's the whole deal with iron. And again, why exactly, I don't know. I'm not a chemist. I don't even pretend to be a chemist. But I just do know that at that point, yeah, we're done. We're not going to get any more out of it. Anyway. All right, so that's a little bit about fission and fusion, and those are the two primary nuclear reactions. Obviously, there's also the, like we were talking about, the decay processes before. But basically, whenever you hear nuclear reaction, at least in the context of physics, we're just talking about something that's going on that's causing a change in the nucleus. And that's why decay is still a nuclear reaction, because we're changing our nucleus, right? We're changing it into something else. All right, anyway, so a little bit about nuclear reactions. Let's see.
Are we able to do fusion in a lab?
So, okay, so fusion, can fusion be done in a lab? Yes. It can be done, and it has been done. But the search is for what we call cold fusion. And cold fusion is one that can be done without like a huge input of energy. Like all of the fusion that we've been able to do on Earth requires more energy than we get out of it, which means it's kind of useless as an energy source, right? If we have to put in more energy than we're getting out, then what's the point? But the goal is to look for, when we say cold fusion, that's when that doesn't require like a sun kind of situation. So has fusion been done? Yes. Has it been done in such a way that it's feasible for creating energy? No, not yet. If you figure that one out, guaranteed Nobel Prize, and you will be probably the richest person on Earth. At least if you're smart about it. If you don't give away all your, intellectual property rights.
That's a thing?
What?
Intellectual property rights?
Yep. Yeah, for example, if I were to, let's say I used my work with you guys to write a book, the college actually owns the right to it because they paid me to do this job, and this job is what let me do that book. Right? So with things like it's a weird thing. Like when we go on sabbatical, every once in a while we get sabbaticals. And if that project, if you decide on your sabbatical, you're going to write something, the college owns it. Because they're, paying you to be off from work, and, what you do there is theirs. So yeah, intellectual property rights are a thing.
So if I want to do something like that, I got to do it at my house.
Yeah. Or I know that sometimes, depending upon, like in science, depending upon who funds you, there are different things about that. So it's not necessarily that you have to do it at your house, but you have to make sure that your funding and your lab situation is such that your work is your work. Another place where that definitely is an issue is in like pharmaceuticals, people that work at pharmaceutical labs. all that stuff's owned by the company. You know, anything they do. So you can still get the credit for it, right? You can still get your Nobel Prize for, you know, discovering the cure for cancer, but somebody else is going to own it most likely. So, yay. And another reason I didn't want to be a scientist. I don't want to have to deal with that. So.
Do you know why they use radiation to, you know, kill cancer cells?
Other than the fact that it kills it?
Yeah.
No, I mean, I think one of the reasons that radiation is a popular method for attacking cancer is that you can direct it. You can actually really target where it's going, as opposed to like chemotherapy, where, you know, they're injecting whatever into you. That's going to go through your entire system, where radiation, they can target the specific location of the cancer cells. You know what I mean? Like if I've got, say, cancer on I've got liver cancer, let's say, and there's a piece of my liver that's got a tumor. Instead of filling my body with drugs that are going to hit everything, my heart and my brain and my skin and everything else, they can target that radiation, send it just specifically to that one spot so that there's less damage elsewhere. But there's going to be pretty significant damage anywhere the radiation itself goes. So think about it this way. What it's basically doing is I mean, if you want to think about it, it's burning the cancer. Because those particles, when they do radiation therapy, it's some combination of alpha, beta, gamma, you know, and all that. Those things have lots of energy. And that energy is basically burning those cells. It's destroying those cells by giving it way too much energy. So that's the whole point of radiation therapy for things like cancer.
It's crazy.
Yeah, and actually they've known about that for a long time. Back when Marie Curie discovered radium, so what was that, like the 1880s, maybe 1890s? They actually already saw, they noticed that this radioactive material could actually assist with cancers. So they were already looking for radioactive material. So they were already mining things like cesium and stuff like that back then, as a cure for cancer. They didn't realize that it was also so dangerous. So I think that back then they probably were killing people with radiation instead of letting them die from cancer. But as the years have gone by, we've gotten a little bit better at it. So anyway, weird stuff for sure. All right, so let's move on. Let's go to particles. Let's start talking about all the other things that are out there that are not in the nucleus. Like right now, we pretty much have, if I were to ask you about the particles that make stuff up, we've got three, right? We've got protons and neutrons, because those are the things that are in the nucleus. And then we got the electrons. We now have seen some other particles, right? Positrons, neutrinos. But there are very, very many others that are out there. And so we should probably talk about them. But before we talk about them, let me just sort of remind you about the different forces that are out here. Okay, so let me just clear this real quick. Now, we're going to talk about the four fundamental forces. because physicists have kind of broken everything down into 4 fundamental forces. So in no particular order, actually, they're going to be in a particular order. We've got gravity. Now, gravity is the first one that you ever learn about, right? We experience that every day, so we're kind of used to that one.
It's my favorite force.
It is your favorite force. It's the one that whenever you're asked, okay, so what forces are being applied, and you just go to the automatic gravity, right? We know that there's always gravity. All right, now it turns out that gravity, though, this is very weak. Compared to the other forces, this actually is very weak. We don't think of it as weak because of the fact that it kind of drives everything we do in life. But if you were to take, let's just say we've got 2 protons. These are going to be our things that we're going to allow the different forces to act on. Two protons at a set distance, the gravitational attraction between them is way smaller than the electromagnetic. It's also way smaller than the strong nuclear force when they're close enough for the strong nuclear force to act. So if we're in a situation, all things being equal, gravity is actually very weak, and it's the weakest of all the fundamental forces.
I have a question about that,
Sure.
though. Is that necessarily true, though? I mean, in most cases, yes, it is, but not in every case. Like, black holes.
Okay, so in a black hole, gravity is still a weak force. I know that doesn't feel right to say, because you're like, yeah, but it's a black hole, nothing can escape from that gravity well. The only reason that there's so much gravitational force is because there's so much mass. But like, if we're gonna like do a real comparison, we have to do like mass to mass comparison, distance to distance comparison, all that. Gravity is weaker by far. Meaning, if you could, like if there were a force that was going to cause what's at the inside of a black hole to want to push apart. So let's say that a black hole was made up entirely, its mass was entirely made up of protons. Right? Those protons don't want to stick together because of the electromagnetic force, the Coulomb force. That Coulomb force would actually start overcoming gravity and start pushing them apart. Unless those protons were so close to each other that the strong nuclear force came into play, because it's actually stronger than the electromagnetic force. But what's inside a black hole is probably not just protons, right? There's going to be all kinds of other stuff in there as well, which is going to help balance out some of those forces that are trying to push them apart and all that. But no, I am very happy with my statement of gravity is very weak. It just is. If we're going to talk pound per pound, it's very weak. We just think it's a big deal because we're next to this really large object. This really large object that's able to exert a lot of force on us because it's so large. But if we just, compare it in a good apples to apples kind of comparison, nope, not even close. Now I'm going to leave a spot here for number 2 because I'm going to introduce you to something else in a second. The number 3 one here, I'm going to put electromagnetic. All right, the electromagnetic force. So you know this one as well, and it's a lot stronger than gravity, but it's not the strongest of the forces. The strongest of the forces is the strong nuclear force. And we know that this is strong, here, very strong, because it can overcome the Coulomb force to keep protons next to protons. Right? That's how we know when something is stronger than the other, is that if it can actually overcome it. And the way that I wrote, remember I said I was going to write this in no particular order, and then I decided I would. These are written in order from weak to strong. Okay, so the weakest is gravity, the strongest is the strong nuclear force. All right, so that does leave one other force that you've not seen before, or we haven't talked about. And it is another nuclear force, but this one is what we call the weak nuclear force.
Nice.
Yeah, I think finally, Ralph just put imaginative names. Yeah, I think what happened was finally, they're just like, oh, fuck, we got to name another force. Well, this one's not very strong. All right, it's the weak force. Cool. We got a strong force. We got a weak force. Yeah, that works. Anyway, yeah, I think they got to a point where they just started. Well, just wait. We're gonna start talking about some other things and get some really strange, odd names. But anyway, so the weak nuclear force. Now, this is another one that goes over very short distances. It only affects things on distances around, like, 10 to the minus 15 meters, femtometers. So things that are about the size of nuclei. All right. So this is same as with the strong force, right? The strong force applies to that same kind of distance. So remember what the strong force does? It's the one that really it keeps those protons and neutrons stuck together, right? So in the nucleus, it holds them. But it doesn't actually affect everything. Electrons don't get affected by it. They're way the hell out anyway. But even when they get close, they don't really affect it. Neutrinos aren't affected. That's why they're able to escape during decay processes and stuff like that, right? Now, the weak nuclear force, it's way weaker. It's like, I want to say the number I learned, and I could just be making this up, but I want to say it's like 1,000,000 times weaker than the strong nuclear force. All right, so it's super, super, super weak. But what it does is it plays a role in some of those decays of the elementary particles, right? Like when we have the beta decay, for example, and that proton turns into a neutron, or a neutron turns into a proton, that's because of the weak force. All right, so it's one of those things that, while it doesn't seem like it's very important, it's kind of a big deal with some of the decay processes, which means it's a big deal, like in, I don't know, the sun, with all that fusion. Because remember, in that fusion we saw there was one stage, the heavy hydrogen plus hydrogen, that ended up going through a beta decay. All right, but anyway, so that's the weak force. But it's also really, 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 really small distance. But that's what's going on the inside. Now, the reason I wanted to kind of talk about all these, or at least bring them up, is that when we start classifying particles, a lot of the particles are classified by which forces interact with them, right? Whether they get subject to, say, the strong nuclear force, or are they affected by the electromagnetic force and things like that. And there are also particles that are the carriers of these forces. Okay, so these are things that basically take how do I want to say this? I mean, they are the carrier. They are the messengers. They are the ones that are like, ooh, I am the carrier of electron or of electromagnetic force, or I'm the carrier of gravitational force, or whatever. Okay, so let me start introducing you guys to some particles. The first ones, I mean, we already know about things like the electron and all that, but we can break these things down into groups by names. And so the first one I want to show you are the group that we call quarks. Actually, no, hold on to quarks for a second. Let's start with leptons. Okay, now leptons are very light, very small particles. Some you've met. Electrons. These are leptons. All right, this is one of the lepton groups, are electrons, and then also neutrinos. So you've already seen those guys, but here's the deal about neutrinos, is that there are three types. There's what we call the electron neutrino, the mu neutrino, and the tau neutrino. Okay, so there are three different neutrinos, and they are formed when these other things are formed. So like the neutrino we were talking about with beta decay, that was the electron neutrino, because it shows up with the creation of electron. There are some other particles. There's one called the muon. When that's created, we get the mu neutrino. It's also sometimes called the muon neutrino. I just call it the mu because there's also a tau particle. The tau particle, when it gets created, we get tau neutrinos as well. Okay, so there are a bunch of different kinds of neutrinos, but as a group, the neutrino that is a lepton. All right, so those other guys, the muon and the tau particle, these six form the group that are called leptons. And they get this name because they mean lepton, it comes from, I believe it's the Greek word for light. And I don't mean light as in shine, the shining light. This is not heavy. Okay, so these guys are called leptons because they're not very heavy. There also are a set that are heavy. They're called hadrons, and we'll talk about those in a little bit.
I have a quick question.
Go for it.
You know, electronegativity of atoms. What kind of force is that? Is that an E&M or is that a weak nuclear?
So that would be electromagnetic.
Okay. Because it wants to resolve its charge, right?
Yeah.
Okay.
Yep. Okay. So the other thing that's special about leptons, as opposed to the other small ones, because there are some other small ones that we're going to see, the ones that I called it, that I mentioned were the quarks. The other thing about leptons is that they don't actually get affected by the strong nuclear force. So let me write that here. These do not interact, or no, I don't want to say it. That's not how I want to say it. Hold on. It's not that they do not interact. They are not affected. Okay, so the leptons, even though they are light, these guys, they're not affected by the strong force. All right, but there are light particles that are affected by the strong nuclear force, and those are the quarks. So let's talk about those guys for a second. So we'll make another list here. And these guys are called quarks. All right, so quarks actually get their name from a poem. I think it's Jabberwocky. In there, it's a nonsensical word, but when they were developing the idea of quarks, it was so nonsensical that someone proposed this as the name, and they went, yeah, that sounds good. Okay, now quarks, these things are also very light. Again, I mean not heavy, right? So these are light particles, but they are affected by the strong force. So that's what makes them different from the leptons. Okay. But in terms of quarks, there are 6 of these. All right, so there are 6 types of these, just like there were 6 leptons. There are 6 quarks, and they are called, ready for this? Up. If there's an up, there's a down. Okay. There's also top. If there's a top, there's got to be a bottom. And then there's one that's charm. And there's no good buddy name for charm. The other one is called strange.
Nice.
So I'm not making this up. Okay. This is not me just like, oh, it's the last week of class, I'm going to give them all kinds of crazy names and they'll buy it. And then when they go and transfer, when Bradley's at UNR and he's like, oh yeah, I remember we were talking in physics about the strange quark. And everybody looked at you funny. Right now. No, they're up and down, top and bottom, charmed and strange. All right, this is their names. Now, the deal about quarks is that these are the building blocks of protons and neutrons. So protons and neutrons are actually built out of quarks.
Are we sure?
As sure as we are of anything at this point.
Okay.
Because all right. This is what we call the things that seem like they need to be the building blocks of protons and neutrons and these other heavier particles. Because here's the deal. They cannot exist on their own. Which now really validates that question that Bradley just asked when we say, really? Are we sure? Because how can you be sure if you can't even see them on their own? Right? It'd be like, so you all know Legos, right? The building blocks. It'd be like, all right, so I've got this thing made out of Legos, but if I take it apart, those Legos don't exist anymore. Right? I mean, that's in essence what we're saying here, is that you need these quarks to put together to form a proton, right? So here's this proton made of quarks. But if I try to break it apart and just see the one quark, nope, everything goes away.
That's a tough one to swallow.
It definitely is. It definitely is. All right. Now, the thing about quarks, see, is that they all have charge. They have charge just like anything else, but their charges are fractional. You heard me right. They have fractional charge. That would be why they can't exist on their own. But like these three, up, top, and charm, these all have a charge. And when I say charge, I mean electrical charge of plus 2/3. So proton has a charge of +1, electron has a charge of -1. Well, these have a charge of 2/3. The others, the down, bottom, and strange, they all have a charge of -1/3. All right, now let's think about what we would need then to say create a proton. So if I'm going to get a charge of +1, that means I need to have, well, at least 2 of the quarks from that top shelf, right? So to get a proton, I need to have 2 of these things at least, because one of them is not enough. But if I have 2 of them, what's my charge now?
4/3.
It's 4/3, which is too much. So what I need then is to lose a third, which would be where one of the ones in this bottom row come into play. All right, so here's how this works. A proton, this is formed by 2 ups and 1 down. So if you take 2 up quarks and 1 down quark, you put them together, you get a proton. All right, now for a neutron, we need a charge of 0, which means any positive has to be balanced by a negative. And you can see the easiest way to do that is to have 1 from this top list and 2 from the lower list. And in fact, that's what a neutron is 1 up and 2 downs. So actually, originally, when they proposed the idea of quarks, they were only up and down. And they thought about it this way. As they started looking at more particles and seeing more interactions between them, they started realizing that they had to create some new properties. And those new properties got wrapped up into new quarks. And so we got this bigger list. All right. So everything else that we're going to see, all the other bosons that we see later, the hadrons, they're going to be made, or not the boson, but the hadrons, they're going to be made up of different combinations of quarks. But all quarks have these charges. Now, another quantity that we have talked about are the spin numbers. Remember spin, we had spin on electrons. Quarks have spin as well. And their spins are also 1/2. Just like with the electrons and stuff like that, the quarks can have a spin number of 1/2. Okay, so quarks actually are affected by all of the forces, and they are, like I said, the building blocks of these guys. Now, here's what gets kind of interesting if you think about this a little bit. Go back to beta decay, because what happens in beta decay?
Neutron becomes proton.
Okay, so either a neutron becomes a proton, or a proton becomes a neutron.
Yeah.
Right? Okay, so look at it in terms of quarks then. Right? If we come back here, think about this. When we went through beta decay, basically what happens is one of the ups becomes a down, or a down turns into an up. Now, if you're still like, oh, I don't like that at all, you shouldn't like that proton just magically turns into a neutron anyway, right? But if we kind of break it down further, that's what's going on here with the quarks, is they're going from up to down or down to up. Okay, they're changing.
See, the thing that I'm thinking now is like, how does something change its charge? Just like that, you know?
Well, I mean, yeah, I don't know. But remember, we're also creating other particles. So it's not like it, like maybe the better way to think about it, and when you get, well, it's changing its charge, it's giving its charge to something else. Because don't forget, when we do that, we're also sending out electrons or positrons that have charge. So that's how I tend to think about it, is it's not so much you're changing your charge, is you're giving your charge, it's giving its charge to something else, or it's taking on the charge of something else. And that we see all the time, right? Think about when you come up in the wintertime and you get static electricity and you zap somebody, you just gave them charge. So transferring charge happens all the time. So I don't really have, for me, I don't have that as the issue. Like here, the bigger issue is, how is it that an up quark turns into a down quark? You know, what the hell does that even mean? But also, when we get to this and we're talking about quarks and all that, a lot of this is just made up. And what I mean by that is, like, we scientists, humanity, needed to create a model to describe what we were seeing. And just saying we have protons and we have neutrons wasn't enough. And so the next obvious thing is to say, well, protons and neutrons are made up of things. What are those things? Well, okay, we're just going to call them quarks. But then what properties do these quarks need to have so that this model explains what we see? Oh, okay, well then we need the up quark to have a charge of +2/3 and a down quark to have a charge of -1/3, so that we can take 2 ups and a down and make a proton, and 1 up and 2 downs and make a neutron, and there you go. So that's the other thing to realize here, is that, I mean, I don't want to say that this is just all BS, because it's not. But we are struggling to make a model that we can understand and comprehend for something that we cannot even see and therefore can't understand and comprehend. Does that make sense? Kind of what I'm saying there? Like,
Yeah, and it's a little sad.
well, like, we're getting to the point now, like, where you guys are in your physics education, you're getting to that point where we're running into we can't see it. We can see the effects of it. We can know that there are things going on, but we can't like put it in our hand. You know, and I mean, even in that regard, like think about electrons. Are electrons even actually there?
You know, I was thinking about that just a little bit ago because I'm thinking I'm trying to relate this to chemistry because I took chemistry, and literally all chemistry is the interaction of electrons between atoms, and yet you just asked that question. I don't know.
Well, I mean, think about where we have a wave function for the electron, and that wave function tells us where we're likely to find an electron, but are we ever like, is it ever actually in one place? And then we get this weird, you know, Schrodinger's cat nonsense of the electron is and isn't at the same time, but then as soon as it's measured, then that measuring determines which one it was. I mean, it's like, okay, is all this stuff just made up? But at some point we go, no, it can't all be made up because like, no matter what they may say in the Matrix, there is a spoon, right? There is a spoon in my hand. Or maybe we are in the Matrix world, and what we have to really understand that there actually is no spoon. You know, like I don't know. I don't know what to tell you. But this is where, for sure, philosophy and science now come together again. And we're like, well, I don't know. But here is what physicists are doing to best describe what we see and best describe what we know is occurring, even though we don't necessarily know. Anyway, I don't know if that makes y'all feel any better or not, but well, there you are. All right, well, I want to share one more thing with you before we go. I gotta see if I can find this on my millions of pages here. Ignore this Adobe thing. That was me missing something. I want to play for you the Quark Song. This is kind of a fun little song about the different kinds of quarks. And after we talk about this later, some more, this will make sense. But let me go ahead and play this for you guys. And I think I've got it set. You can hear volume. Can you hear the volume?
Yeah.
Okay.
Quark is a fundamental constituent of matter observed in 1968 through deep elastic scatter. We found that protons aren't as simple as we thought. We thought they were solid particles, but they are not. Protons, in fact, are made up of three separate pieces. It just gets more confusing as our knowledge increases, but that is what a quark is. It's a piece of a proton, and they also make up other things, including the neutron. Oh, down strange charm. If you don't know what a quark is, it don't matter, you still got them. And with leptons and protons and something the mist, they make up everything that we can see and that we know exists. Things made up of quarks, including protons and neutrons, are composite particles that physicists call hadrons. Many types of hadrons are theoretically described, but most exist for only very brief amounts of time. Quarks have electric charge, color, charge, mass, and spin, and having color charge exists solely inside of other kinds of particles and cannot exist alone, which is why quarks have never been studied on their own. Down strange charm. If you don't know what a quark is, it don't matter, you still got them. And with leptons and protons, unless something the mist, they make up everything that we can see and that we know exists. Quarks can join together in two different ways. Baryons and mesons, but most instantly decay. If a particle has three quarks, then it's a baryon. And if there's one quark and an anti-quark, then it is a meson. These tiny bits of matter are part of almost everything, and there is no unified theory to make it less confusing. But the fact that we've identified that they exist at all is so goddamn remarkable that I just sit in awe. Oh, up, down, strange charm. If you don't know what a quark is, it don't matter, you still got them. And with leptons and protons, unless something the mist, they make up everything that we can see and that we know exists. I like that song. It's a good song. I think you all would play it too. And you can listen to it anytime by going to bft.va/quarks. Good morning, John.
I meant to hit pause. All right. So there was actually a lot in there that we haven't talked about. But you may have noticed that there are some different kinds of classifications of particles depending upon how many quarks are in there. There are also anti-quarks. Haven't talked about those yet. And they also talked about color charge. There is a color to quarks. We'll talk about that as well, but I think we'll save that for next time. So we're going to leave it here, but on Thursday, we'll talk more about the different characteristics of quarks, how they're combined into the different particles, whether we're talking about baryons or mesons. And then we'll talk about the bosons, which are the things that actually do the communication for the forces. So we'll spend a little bit more time talking about particles, and then we'll just kind of wrap everything up. All right. So I think with that, so Victor just put in the chat, now I understand why they say, if you think you understand quantum mechanics, then you don't. Yes, that's absolutely true. All right, so with that, we'll go ahead and stop for today, but we'll do our best to wrap up on Thursday, all these sort of untied strings. We won't be able to tie everything together because, as Victor said, if you think you can, you can't. So, all right, so everyone have a great couple days. I'll see y'all Thursday.